So I'll try to show the procedure through a numerical example. You can follow something similar for the assignments on velocity and acceleration analysis. Essentially, in this problem, there is this linkage. There is a ternary link with three nodes, which is BDC. There is essentially a slider crank plus a 4-bar mechanism. If you can see, from A, B to C is a slider crank, and then from C, D, E, F you can see a sort of a 4-bar linkage. There's information given about omega 2. There's no alpha 2. It's set to 0. There's a clockwise 60 RPM rotation given to the second link. We have various link lengths given in inches. Not that it matters. You could very well take this as centimeters and you'll most likely get similar results, except the units will change. The point F has been specified to be at the coordinates 3.75 inch, comma 0.75 inch. And the question is to find acceleration of C and angular acceleration of link 6, which is, so the numbering goes like this. This is ground is link 1. This is 2, this is 3, this is 4, this is 5, and this is 6. So link EF. So essentially, we will have a position diagram drawn, which will allow us to measure off. If you're following the graphical method, it will allow us to measure off these angles, various different angles, and then we can proceed to velocity analysis. You will draw this velocity of B with respect to A, and that would be orthogonal to the link AB, and the magnitude of VB is simply 1.5 inch times 60 RPM. So the RPM has to change to radians per second. 60 rotations per minute is equal to 60 divided by 60 is 1 rotation per second, which is equal to 2 pi radians per second. So effectively the omega 2 is approximately 6.28 radians per second, and so VB magnitude is about 9.42 inches per second, and we know it is normal to AB in terms of the direction, and we know the sense because of the RPM is given as clockwise. From there, we can draw a line which is parallel from this point, parallel to the sliding axis, and then we can draw something which is perpendicular to BC, which will give us the velocity at which the slider is moving. So this is V of C. This is V of C with respect to B. Then again, now we can measure these off from the diagram if we're trying it to scale. The next thing we can do is we can consider what is velocity of B with respect to C, and then because this rigid body BCD has to have similar velocities, we can draw a triangle. We can identify this point D such that we can draw a triangle which is similar to BCD, and from that we can obtain, if I can, let me zoom this in slightly just to explain what I'm saying. So this is velocity of C with respect to B. You can identify a point here such that this triangle, you can look at this point D. This triangle is similar to this triangle. So you know the length of BC, you can measure off the length of this velocity vector, and you know the length of CD, so you can measure this line and identify what is the velocity of this point D. In our usual procedure, we can find V C with respect to B, and we can divide that by the length CB to obtain omega 3. Then we can write VD with respect to B is equal to the length dB times omega 3. Once we know the direction, we can identify what are the um, velocities in which sense they are moving at this point, specifically here. Then from here, we know the velocity of this point E has to be perpendicular to DE. We'll draw it with a different color just to keep it distinct. And then we also know that for the uh, point E with respect to F, the velocity has to be perpendicular to EF. So we can draw that line as so. So this becomes point E, and this is the velocity of point E with respect to the origin of velocity diagrams or global coordinate system, and this is the velocity of E with respect to D. This is velocity of E. You can measure these off from the velocity diagram drawn to scale, and then obtain what is um, each of these velocities that we are looking for. Thereafter, we can identify various accelerations. At this point, I might have to just, okay, I can copy this diagram. I'll paste it here. And let's look at we can identify from the velocity diagram the omegas of link 5, 6. We already got the omega of 3. 5 and 6 we can obtain based on VED magnitude divided by DE, and this would be EF magnitude divided by the length EF. These are all now known quantities. Then we move to acceleration analysis. We get the acceleration of point C should be equal to acceleration of B plus acceleration. Of course, this will have normal and tangential components. And then you can add from C with respect to B tangential plus C with respect to B normal. We know this quantity, this is 0 because there is no alpha. And then we know this quantity, we need to know this. So we don't know this, but we know this. So we can draw the acceleration diagram. This is acceleration of point B normal. We know there is no tangential acceleration to point B. So we can then go to acceleration of C with respect to B. And it goes in this way, acceleration of C with respect to B. This is normal. And then the tangential component of that should be perpendicular. So we can draw that line which is perpendicular and will along which the tangential acceleration of C with respect to B will exist. We can draw a horizontal line because we know the slider is going to have acceleration in the horizontal direction, and thus we have identified A of the point C. We can measure this, and we have one of the answers that we were looking for. This is the other part, which is acceleration of C with respect to B tangential. From the acceleration of C with respect to B, we can draw a triangle similar to the previous case. We can draw the acceleration of C with respect to B total. From there, we can draw, so this is B, C, we can draw something like this. This would be the point D. Maybe we'll just mark it with a lowercase letter. This is D, this is C, and this is B. So from here we can draw acceleration of E with respect to D normal. That's something which will be orthogonal, which will have the tangential component of acceleration of E with respect to D. From here, we can draw acceleration of E with respect to F, which is along this line. This is acceleration of E with respect to F normal. And then we would be able to draw something orthogonal to that, which has, this is line of acceleration of E with respect to F tangential. This is line of acceleration of E with respect to D tangential. So we can find that this is the intersection. So we get this line. This is acceleration of E with respect to F tangential, which should be equal to EF times alpha 6. So we can find alpha 6 from here. And that's essentially the solution of this problem. If you are drawing these to scale, you can measure various lengths of these vectors, and using the scale, you can directly identify numbers. If you're doing a computer program, you need to read off the coordinates and write expressions for distances. Instead, if you're trying to follow analytically, or you're trying to use algebra from this geometry, then it becomes a tedious task unless the angles are nice, where you can directly find using cosine rules or sine rules what are the other lengths or angles.